We studied transferability of graph filters to show that graph filters are transferable across graphs that are drawn from a common graphome. The first point to emphasize is that in the previous sections, we have shown results that hint at transferability, but we have actually not proven transferability. We have instead proven that graph filters can be close to graphome filters under some conditions. Indeed, our results look at a graph Gn with n nodes sampled from a graphome W, and claim that the graph filter h of Sn running on the graph Gn is close to the graphome filter Th running on the graphome W, if the filter coefficients are the same in both filters. A legitimate transferability claim requires that we compare two different graphs, possibly having different numbers of nodes, and that we show the corresponding filters to be close. Namely, we have to consider graphs Gn and Gm, both sampled from the graphome W, and have to show that the graph filters h of Sn and h of Sm are close. It is easy to see that this is true given what we know about the similarity between both graph filters to the graphome. We know that the h of Sn is close to the graphome filter Th, and we also know that the graph filter h of Sm is close to the graphome filter Th. From these two facts, it follows that the graph filter h of Sn is close to the graph filter h of Sm. This is just the triangle inequality applied to the comparison of the filters via their relative comparisons to the graphome. To state a formal theorem, we begin with a formal problem formulation. We are considering the graph signal Snxn along with the graph signal Smxn. Both of these signals are sampled from the graphome signal Wx. The samplings are different as they contain different numbers of samples. We then consider a given set of filter coefficients hk and process the signals on their respective graphs. That is, we run the filter with coefficients hk on the graph Sn to process the signal xn. This is done with a polynomial on Sn modulated with coefficients hk. This produces the signal yn. And we also run the filter with the same coefficients hk on the graph Sm to process the input signal xm. This is done with the same polynomial but instantiated on the graph Sm. The output signal is ym. We want to compare the output signals yn and ym. Since they have different numbers of components, we do not compare them directly. Rather, we compare the induced graphome signals uppercase yn and uppercase ym. Our transferability results require the same set of assumptions we used when comparing graph filters to graphome filters. This is a triplet of Lipschitz assumptions that we repeat here for reference. We require the graphome to be Lipschitz with Lipschitz constant L1, the filter's frequency response to be Lipschitz with constant L2, and the graphome signal x to be Lipschitz with constant L3. Of these three assumptions, it is HU, the Lipschitz continuity of the frequency response of the filter, that is fundamental. The other two assumptions are necessary, but they are not conceptually that important. We also require the same pair of definitions we introduced when comparing graph filters to graphome filters. These definitions require that we fix a bandwidth C to separate eigenvalues that are close to 0 from those that are not close to 0. Associated to C, we define the C-band cardinality B and C. This is a count of the number of eigenvalues whose absolute value is larger than C. This is a number we know is finite. Also associated with C, we define the C eigenvalue margin of the graph Gn. This margin is the smallest gap between a graph eigenvalue lambda ni and a graphome eigenvalue lambda j, with different index. The graph eigenvalue has to be in the C-band, but the graphome eigenvalue can be anywhere. Typically, this gap is the difference between the graph eigenvalue that is immediately above C and the graphome eigenvalue that is immediately below C. With these set of assumptions and definitions out of the way, we can state the graph filter transferability theorem. Consider then graph signals Snxn and Smxm sampled from the graphome signal Wx. Further consider the corresponding filter outputs yn and ym. The outputs are the result of processing different signals on different graphs. but they both use the same set of filter coefficients. If assumptions A1 through A3 hold, and considering definitions D1 and D2, the difference between the norms of the induced graphene signals Yn and Ym is bounded by the expression shown on the slide. There's a lot going on in this bound. We have terms that depend on the number of nodes of the graphs. They are sums of inverse square roots and vanish as n and m grow. The summons are scaled by the Lipschitz constants of the graphene, the filter's frequency response, and the graphene signal. We also have terms that depend on the bandwidth C, along with the corresponding C-band cardinalities and the C eigenvalue margins of the graphs Gn and Gm. The bound depends on the larger of the two C-band cardinalities and the minimum of the two C eigenvalue margins. We pick the worst of the two in each case, the one that makes the bound largest. And we also have the norm of the graphene signal X appearing on the bound. The proof of the theorem is a simple application of the triangle inequality. You can find it in the lecture notes that are available in the course's website. More important than providing this proof is to explore the effects of the different terms that appear in the transferability bound. We do this in the next section.